turns out to not be mathematically rigorous, but we're not yet ready for mathematical rigor here. We need some other mathematical tools before I can rigorously prove this. We need a whole bunch of mathematical relationships that we'll find in chapter 3, which we don't have yet. So I'm going to do this quick and dirty, and for those of you that really understand your calculus, you'll understand that this is not right. But it turns out you get the right equation, but for the wrong reason. I'm going to divide through by dt, and I'm going to say I'm doing that at constant pressure. So I say du divided by dt under conditions of constant pressure. So far, that's absolutely correct. That equals pi t times dv over dt under conditions of constant pressure plus cv. That equation is absolutely correct. Now I'm going to say that that's the partial derivative of u with respect to t at constant pressure. Now this is partial of v with respect to t at constant pressure. Do you buy that step?
No.
You shouldn't.
Okay.
That's not precisely rigorous. But it turns out it gives us the right equation, and we can, in fact, prove what I'm going to give you with more mathematical tools. Just our toolbox is a little bit empty right now. We don't have the tools we need. Turns out we've seen that before. Alpha, the coefficient of thermal expansion, was 1 over v, partial of v with respect to t at constant pressure. So that derivative is equal to volume times alpha. Simply multiply that equation through by volume. And we can get, substituting that in,
Dr. Steph, what's on the other part of the division sign, please?
excuse me?
You have delta v over the derivative v over the derivative t in respect to t divided in back further.
She wants the previous page, Dr. Scott.
That is
She's
the
got,
previous
he's got the
page.
thing.
Still not sure what you didn't get, but
Okay.
it should be there.
I got it now.
So we can generate that equation simply substituting v alpha for that derivative. If Joule is correct, the internal pressure is 0. That term becomes 0, and partial u with respect to t at constant pressure equals CV. That's sort of an interesting relationship. Well, Joule is not correct, but is he for a perfect gas?
Yes.
Yes, because a perfect gas by definition has no intermolecular forces. So we can say that for a perfect gas, and that is correct, for a perfect gas, that relationship holds. Except that CV was partial of u with respect to T, not at constant pressure, but at constant volume. That's the definition of the heat capacity. So what we've just shown is that partial u with respect to T at constant volume is for a perfect gas equal to partial U with respect to T at constant pressure. That's a little surprising. We take the derivative, it doesn't matter which we hold constant. This gets us to another interesting situation. If we come back and look at the difference between the two heat capacities, Cp and Cv, Cp is partial H with respect to T at constant pressure. Cv is partial U with respect to T at constant volume. But if we take this, we could write this, we could say this is also equal to partial H with respect to temperature at constant pressure minus partial U with respect to temperature at constant pressure. I think I better go to the next page so you can see things. 2 seconds is up. Need to learn to write partials faster. Okay. I'll just rewrite it up there. But H is U plus PV. That's in fact the definition of the enthalpy. So the partial of H with respect to temperature at constant pressure is equal to the partial of U with respect to temperature at constant pressure plus the partial of the product of pressure and volume with respect to temperature at constant pressure. Well, at constant pressure, the pressure comes out of that. How do we get D